Hi, today I want to talk about chemical bonding, which is come under structure 2.4.1 and structure 2.4.2 of IB chemistry. All I want to mention very quickly the three bonding type that we all know, ionic bonding, covalent bonding, and metallic bonding, with the definition, how these bonding are formed, and some of the properties of each type of compound. So ionic compounds have high melting points, they are brittle, they are soluble in water, and they conduct electricity only when they are molten and when they are dissolved in water. For covalent compound, they have low melting and boiling point. They do not conduct electricity and they are not soluble in water, except for some cases. Now for metallic compound, they are malleable. They conduct electricity because of the presence of something that we call the sea of electrons, which are delocalized electrons that can move freely around the positive ions of metals. But what I want to focus on today is that real bonds often have something called mixed characters. So polar covalent bond can have partial charges. They do have partial charges. Even ionic compounds have some covalent characters. So bonding lies on something called the continuum between the three extremes. That's why we introduced something called the bounding triangle. This is the bounding triangle. You can find it in your data sheet of your IB chemistry. It's also called the Van Arkel-Ketelaar bounding triangle. This bounding triangle shows us the bounding as a continuum. We have two axes. X-axis is showing the average electronegativity, and this is the formula calculating the average electronegativity between the two atoms. It's the electronegativity of the first atom plus the electronegativity of the second atom divided by 2. And now in the y-axis, we have simply the difference in electronegativity between the two atoms. So this is it. This is the formula calculating the difference in electronegativity. So just we subtract the two electronegativity. In the top here, we have the ionic bonding. Here we have the metallic bonding at the bottom left, and in the bottom right, we have the covalent bonding. Let's take cesium fluoride as an example and try to solve and find the bonding inside cesium fluoride. So we start by the first one, which is cesium, and you have also in your data sheet the electronegativity periodic table, the periodic table showing the electronegativity of atoms, so you can use it. You can directly get the electronegativity of cesium and the electronegativity of fluorine. So the first step, the electronegativity of fluorine is 4. So the first step is to calculate the average. You add the two numbers together, 4 plus 0.8, and you divide it by 2. This is the answer. So this is the average. The average, as I said, is on the x-axis. So we go to the x-axis and we search where we can put 2.4. 2.4 is exactly here, between 2 and 2.5. This is 2.4. Okay. Then after 2.4, we have to calculate the difference in electronegativity. Again, the electronegativity of fluorine is half, the electronegativity of cesium is 0.8, and the difference is 3.2. We have to go to the y-axis and plot the 3.2. This is 3.2. Then if we link them together, we'll find a point here. Okay, so this is the top, the exact top of the triangle, which show us that CSF, cesium fluoride, is a around like 100% ionic compound. So this is around like it's close to 100% ionic compound because this is on the top of the triangle. So this is the perfect ionic compound. We can consider it totally ionic. NaCl. First of all, you need to go to the periodic table and get the electronegativity in your data sheet. Electronegativity of Na, electronegativity of Cl. You need to calculate the difference between them, which is 2.1. Just subtract them. The average, add them and divide by 2. This is the average. Let's plot these 2 points on the graph on this inside the triangle. So the electronegativity difference is 2.1. This is 2.1. It's here, and the average is 1.95, which is here. Then you join them together and we obtain a point that is here. This point is around 75%. It's around 75% ionic, 70 to 75% ionic compound. So if we need to predict the properties of NaCl, it has high melting point because it's mostly ionic compound. it conduct electricity only when molten or when it's like dissolved in water. It's a brittle solid and it's for sure soluble in water. So this is easy how we can use and how we can find the percentage if it's mostly ionic or mostly covalent. Now let's check copper. If we go to the periodic table, you'll find the electronegativity of copper equal to 1.9. The difference in electronegativity for sure it's zero because we don't have it's copper 1.9 minus 1.9. And the average is 1.9 plus 1.9 divided by 2, which is giving us also directly 1.9 as average. Let's put them. So we have 0 as electronegativity difference, 0. And then the 1.9 is here, which is for sure going under the metallic bond. So this is a metal. The properties of metal, as we all know, they have high electrical and thermal conductivity. They are malleable, ductile, and they have like a shiny appearance and variable melting and boiling point depending on the. Now let's take another example, which is silicon dioxide, SiO₂. I put this example on purpose because I want to introduce something about the polar covalent, the covalent bond. I need to talk a little bit about the covalent bond. So, as we know, we have to get the electronegativity of silicon and the electronegativity of oxygen, and then we have to do the difference and then the average. The point will be here in the place of the polar covalent. So this is a polar covalent. Now in the next slide, I'll introduce what do we mean by a giant covalent, or what do we mean by network solid, because this is a type of covalent bond where it's looking like this. It's a giant molecule where all the atoms, silicon and oxygen, are linked together in a giant molecule, and they have like we can say like a strong bond between them, strong intermolecular forces, which cause it to have a very high melting point. It's hard, it's brittle, and it's insulator. It cannot conduct electricity, and it's insoluble in water. I want to make sure that you are able to differentiate between the two types of covalent bond. So the covalent, the molecular covalent, which is the simple molecule, the one that we know, H2O, CO2, O2, and so on, and the covalent network, which is a giant covalent, which is the SiO₂ that I just showed you. It's a big giant molecule of silicon with oxygen, and they are linked together with a very strong force. We have also the diamond that is formed by carbon, a lot of carbon atoms that are linked together with a very strong force. These are called network covalent or giant covalent, and it's different in properties than the one that we know, than the simple molecule. Here it has low melting point, here it has very high melting point. This is hard, this is insoluble in water, and it doesn't conduct electricity. So the main difference is the very high melting point and low melting point due to the intermolecular forces, because here it's strong, it's a big network, a giant molecule that are where the atoms are really linked together in a strong force. In this slide, I want to discuss oxide case study. We have some example of oxide compounds like magnesium oxide, aluminum oxide, silicon oxide, phosphorus oxide. First of all, I want to show you the difference in electronegativity between these elements that are the elements of the period 3 of the periodic table and oxygen. So there's a big difference between sodium and oxygen, also magnesium and oxygen, aluminum and oxygen. That's why we can divide these oxides into three groups. Sodium oxide, magnesium oxide, and aluminum oxide will be placed in the first group, which are here in the ionic compound zone. So the bonding, we can say that the bonding in these elements is ionic. They have ionic bonding. Now, we already discussed in the previous slide the case of SiO₂, which is silicon oxide. It has high melting and boiling point, and it doesn't conduct electricity because it is a giant covalent oxide. It's a giant covalent compound. Now, as we can see from phosphorus, sulfur, and chlorine, the electronegativity is becoming less, but the electronegativity difference is becoming less. That's why we can consider these as covalent bond, and they are here in this zone of the triangle, so it's a covalent bond. And they have low melting and boiling point, and they are non-conductor of electricity. Now it's your turn to practice by yourself. I want you to predict the bound character for these four compounds using the periodic table. This periodic table will be provided for you inside your data sheet, and the electronegativity is written down this number. Like the electronegativity of oxygen is equal to 3.4, electronegativity of aluminum is equal to 1.6, of potassium 0.8, and so on. So find the electronegativity here in this periodic table and use the triangle to predict the bonding character for these four compounds. K2O, the electronegativity of K is 0.8, oxygen 3.4. This is the difference in electronegativity, and this is the average. If you put it in the graph, you will find it here. So it's strongly ionic. It's around more than 90% ionic. It has a very high melting point and boiling point. It conducts electricity when molten or when it's dissolved in water. It's soluble in water, and it forms a strongly basic solution in water, and the structure is ionic. Now let's talk about AlCl₃. This is the difference in electronegativity and the average. In the triangle, AlCl₃ will be here. It's showing that it has a polar covalent bond, which will give us a lower melting point than ionic compound. It doesn't conduct electricity, and it's soluble in non-polar solvent. So it's a molecular compound. For today, thank you so much for listening and watching. We still have zinc oxide and carbon dioxide. Think about it, write your answers in the comment, and I'll check it for you. Thank you so much. Bye bye.